Yeah, so good people, in today's session, we are looking at the primary magmas, parental magmas, and the variation diagrams. And the variation diagrams that we're going to be looking at is the Harker diagrams, the AFM, and the QAPF diagram. Okay, so that's what basically we're going to be looking at today. Okay. Now, the parental magma, it refers to the original magma from which a specific igneous rock type is derived. The parental magma, it means if it undergoes what you call magmatic differentiation, such as the fractional crystallizations, assimilations, and other things, you're gonna form different igneous rocks. Okay. So where it is possible to find the primitive or primary magma composition, it is useful to attempt to identify a what you call a parental magma. So a parental melt is a magma composition from which the observed range of magma chemistries has been derived by the process of igneous differentiation. So it need not to be a primitive melt. Okay. So that is a parental magma.
É,
It means, yeah.
o fast.
A
O Grana
or
fast.
okay, it's fine. Now, what I was saying is a parental magma, it's the magma that when it evolves, it's a magma that when it undergoes what we call magmatic differentiation. Magmatic differentiation, we're talking about things like fractional crystallization, assimilation, and magma mixing and other things. So it's that magma that can undergo through those processes. And by going through those processes, it changes, okay? The magma chemistry change, all right? Then now to become different rocks. So for example, if the mafic magma undergoes, or the magma that contain a range of chemical composition from felsic all the way to ultramafic, when now the fractional crystallization occurs, then now it means the ultramafic composition is going to be taken out of the system. Then the magma is going to shift towards the mafic, the composition ranging from mafic to felsic. Then if the mafic crystallizes and we remove them out of the system, or we take them out of the system, the magma is going to, evolve into the one ranging from intermediate to felsic until we remain with the magma and that can crystallize the felsic materials such as the granite and rhyolite. Okay, so that is what you call magmatic differentiation. So a parental magma, that's why we're saying it's the original magma, which a specific igneous rock type is derived. Now the characteristics, it includes the fact that this can be a more evolved composition. Okay, it can be a more evolved composition because of it can undergo various processes or various magmatic differentiation. That's why it becomes the magma evolve from being ultramafic to being mafic, or from being mafic to being intermediate, or being intermediate to being more felsic. Magma changes because of different magmatic processes. Okay. Now, these reflect the changes that have occurred during the cooling and solidification process when when crystallization occurs. All right, when crystallization occurs, the process that can affect that would be, for example, fractional crystallization. That can also make the magma to evolve. All right, but now when things like when the magma pass through the fractures, it can assimilate or incorporate the material from the county rock. Now, if it incorporate the material from county rock during its ascent, then what can it do is it will now change. The chemistry will also change. It will be contaminated. Okay, that is also what you call the magma mixing. Magma mixing also can make sure that now the chemistry of the or the chemical composition of the magma get to evolve. Parental magma can be derived from the melting of the earth mantle or the crust and may include a variety of minerals and chemical components. Okay. Now, a primary magma, primary one is the initial composition of the magma. Okay, is the initial composition of the magma. That is the most important part. The initial composition of the magma. So underline this, initial composition of the magma. But now, this thing must not undergo the what you call magmatic differentiation. Okay, magmatic differentiation. So we are looking at that magma, the initial composition of that magma before it can undergo any magmatic differentiation. Okay, that is to say, before it can evolve. Okay, because of fractional crystallization and other igneous processes. And then they must have the magnesium oxide number or content greater than 10%. Okay, or it must have at least greater than 10% or 10 weight percentage. Okay, that is the two characteristics. The initial composition of that magma, it means when you melting the ultramafic rocks, okay, or the mantle rocks, now you're going to get a melt. That melt, the initial composition of that melt, before it gets to be, differentiating, okay, then now that will be what you call a parental magma. That's why also the initial composition or the initial melt that forms directly from the partial melting of source rocks. It can be mantle and basically mantle rocks, okay? So remember, the mantle rocks, it will undergo what you call partial melting. Okay, it will undergo what you call partial melting. Partial melting, it's a process wherein you are melting a small portion of that rock. All right, you're melting only small portion of that rock, and then depending on the stability of different minerals, following what you call the Bowen's reaction series. We know old people are boring, and then for example, olivines and pyroxenes, all right, amphibole and biotite. And then here we have all my quartz. We have got orthoclase, muscovite, and quartz. So during melting, you are melting the felsic material first, but during crystallization, you are crystallizing high temperature materials first, like olivines and pyroxenes. Okay, so during partial melting of that mantle, the first magma that you're going to form, okay, the initial magma is going to be a parental magma. And then that magma must not undergo, initially when we're looking at it, it must not have underwent what you call magmatic differentiation, okay? So it must not evolve, okay? Then now, but the magma, it must have at least greater than 10% weight or 10 weight percentage of what you call magnesium oxide. Okay? So we know that when a rock melts, the liquid is a primary melt, especially if that melt have not undergone any magmatic differentiation. Primary melts have not undergone any differentiation, and therefore it will represent the starting composition of a magma. That's why we're saying initial composition of a magma, or the starting composition of a magma. But what the only problem is, in nature, this thing, is not doable. All right, but in an ideal world, then it's possible. Okay, in nature, it is rare to find primary melts. They are not prominent. But the leucosomes of migmatite are example of the primary melts. Primary melts are derived from the mantle, as I've mentioned, are essentially important and are known as primitive melts or primitive magmas. Okay, the primitive melts or the primitive magmas. By finding the primitive magma composition of a magma series, it is possible to model the composition of the mantle from which a melt was from. If you want to model the composition of the mantle of the mantle, you can use the primary magma. Okay, so that's why it will be now important, or it will be essential to understand the evolution of the mantle. Okay. Now, the characteristics of the primary magma include being more primitive in composition, means the magma, the composition of that magma has not or did not evolve. Okay, did not evolve. That's why we're saying it's primitive. Okay, and obviously it will be rich in magnesium and iron, because of we know that what you call ultramafic or mafic, where in fic it means iron, and Ma, it means magnesium. So mafic has got high amount of magnesium and iron. And then if we have ultramafics like mantle rocks, obviously they will have a high amount of extra amount of magnesium and iron. And basically those rocks, they are peridotites, for example, they are rich in olivine. They are rich in olivine, which gives a rock a greenish color, like for example in dunite, or dunite, which has got over 90% of the which has got over 90% of the what you call olivine, right? And then but you can also have the pyroxene and also what you call the plagioclase. So how these things they are distributed, they can give you the rocks such as the lersolite, where light has bakite, and the danite, which are the rocks which are different types of what you call the peridotitic rocks. Okay, so these are mantle rocks. It means they've got this magnesium and iron within olivine, pyroxenes, and the plagioclases. Okay, so primary magmas are thought to be the direct products of mantle melting, and are the starting point for the formation of different types of magmas as they rise and evolve. So that's why we say the primary magma represent the starting composition or the initial composition. So far, so good. So far, so good. All right. That's great. Now, another characteristics, obviously formed at greater depth, okay? And then that magma must not undergo what you call modification by either what you call fractional crystallization or assimilation or magma mixing. That's what I said. And then you have highest magnesium number. We have a highest magnesium number, wherein we've got magnesium and divided by magnesium plus iron multiplied by 100. Then this thing, it will give you magnesium number. It will give you a magnesium number. Okay, so the magnesium number of what you call the primary magma, it must be, like I said, you must have the highest, at least greater than 10 weight percentage. Okay, now when we are looking at the lersolite, when we're looking at the experiments of the lersolite melt, we get that the magnesium number, it is between 66 to 75. Then chromium content is 100 parts per million. Nickel is that, and then it's saturated as well. All right. So that's basically what we'll be looking at when we're looking at the primary magmas. All right, it has got high amount of the magnesium, and then nickel, and then we know nickel is there in the rocks which are mafics, or they're associated with the mafic minerals. All right, so you'll find it inside olivines and pyroxenes. All right, so basically that is that about the primary magma. But now, the key differences in terms of origin, obviously the primary magma would be formed directly from the melting of the mantle, and it will represent the original or the initial composition before evolution. But the parental magma is derived from the evolution when you are now evolving the primary magma. Okay, it will be influenced by processes like fractional crystallization or contamination. Okay, now in terms of composition, the primary magma, it will be more mafic, rich in magnesium and iron, and then it's less differentiated, meaning it's less evolved. Then parental magma may be more evolved and can vary or widely in composition depending on the history of the magma. Okay, it can have something ranging from mafic to ultramafic or ultramafic to felsic. Okay. Primary magma refers to the initial melting geological process, whereas parent magma refers to the magma that gives rise to specific igneous rocks after undergoing a various geological process. Okay, so for example, if ever you crystallizing first the ultramafic composition, you're gonna or ultramafic to mafic, you're gonna have the, for example, ultramafic rocks such as the peridotites, like I said, the dunite, the larzolite, in terms of peridotites. Okay. Now, how does the primary magmas form? Obviously, they would form during what you call the partial melting. Okay, partial melting of what you call the primary, of what you call the mantle rocks. Sorry, so mantle rocks such as what you call the peridotites. Okay, peridotites, they are rich in magnesium and iron within the mafic materials. All right, within the mafic materials. So, if you do not have an information about these peridotites, I mean, peridotites are the ultramafics, and they're divided into, like I said, dunite, the larzolite, the whorlite, and the what you call the whorlite. So in these rocks, dunite will have more percentage of olivine. So, but in other rocks, the olivine, it will be absent. Okay, it can be absent or be in less amounts. All right, wherein olivines and pyroxenes are playing the major roles. All right, but in some rocks, the percentage of olivines and pyroxenes, they are uniform. All right, and then sometimes now in other rocks, as Hasbergite, the olivines and pyroxenes, they are very big, and then you'll be able to see them with your naked eyes. All right, basically. But now when you're partially melting the peridotite or a mantle rock, it's going to give you the melt, and that melt, before it undergoes what you call magmatic differentiation, it will represent what you call its initial composition. Before evolution, it would give us what you call the primary magma. Okay, that's why we say when peridotite experiences high temperatures, okay, particularly in areas of the mantle beneath the mid-oceanic ridges, subduction zones of mantle plumes, some of the minerals within the rock start to melt, forming a magma, especially the low temperature minerals. The process of partial melting, it's when you are melting just small portion of that rock, all right? You're not melting the entire rock, but only the small portion. So basically, that's how the primary magmas form. Okay. Primary magmas are usually basaltic in composition and are mostly found in volcanic environments such as the mid-oceanic ridges, hotspots, and the subduction zones. The specific mineral composition of primary magmas is determined by the depth at which they form. As the lower the pressure, the more volatile complex components like water or carbon dioxide can influence the magma's characteristics. Okay. But if we are comparing the primary magma with what you call the basaltic magma, we know the primary magma, it gives us what we call the initial composition of the melt before that melt undergoes magmatic differentiation directly from the mantle rocks, such as the peridotite. Okay, so it will be considered obviously basaltic because of it has got the dark minerals such as olivines, such as basically pyroxenes. All right, or mafic materials like olivine and pyroxenes, and plagioclase, a calcium-rich one. All right. Now, obviously, people they normally confuse the primary magma with the basaltic magma. They are not basically the same. They are not really the same. Okay. So when we are looking at what you call the basaltic magmas, okay, basaltic magma, it describes a magma with chemical composition that is similar to basalt. And we know basalt, it has got dark materials, mafic materials that are rich in magnesium and iron, but which can be a primary magma, but also may also be modified through further processes, or through what you call magmatic differentiation. Okay. So the key distinction lies in whether the magma represents the initial melt from the mantle, which is the primary, or has undergone further composition changes. Okay, like basaltic. So the basaltic, or it will undergo the what you call the it will undergo what you call magmatic differentiation, and then to evolve into the intermediate rocks. All right, and then again also evolve also into the felsic components. Okay, that's what you call a basaltic magmas. In terms of origin, primary magma is the first melt generated from the mantle, whereas the basaltic magma can be derived from the primary melt, but may have undergone some degree of differentiation. Both primary and basaltic magmas are considered to be mafic because they've got high amount of magnesium and iron, meaning they are rich in those elements. But obviously they are having a lower silica content. They're having lower silica content, SiO2, sodium, and potassium as well. Okay, and also aluminium. But variations in the specific mineral proportions can occur depending on the degree of fractionation. Okay, then now, what is the implication of these primary magmas and the basaltic magmas? By studying the primary magmas will help scientists understand the composition of the mantle because you are able to model. Okay, so while analyzing the basaltic magmas can provide insight into the processes that occur as magma rises through the crust, right? So we are checking at the magma evolution. Obviously, when the magma ascends through the crust or through within the fractures, it will undergo assimilation, can undergo assimilation and then incorporate the crustal material. And then by so doing, you can change them. If the mafic material incorporates the felsic content, then it can evolve and then change into it can evolve and change into a more intermediate magma. Right, so usually this assimilation or magma rock interaction, we also see it in the Bushveld complex, wherein and then this contamination, it plays a major role in formation of certain deposit like PGEs. Okay. Primary magmas are the initial magmatic liquids derived directly from the mantle rocks such as peridotites, and that melt must not undergo any magmatic differentiation. Okay, that's why it represents the initial composition. Whereas basaltic magmas are subset of a primary magmas that are rich in magnesium and iron. All right, so it means it's the subdivision of the primary magma is the basaltic magmas. Okay. Now, we also have got what you call the variation diagrams. We also have got what you call the variation diagrams. So variation diagrams is a display of chemical differences and trends shown by related suite of rocks in which the composition variation is a consequence of a fractional processes, either partial melting or fractional crystallization. This according to Wilson in 1989. Okay. So the variation diagrams, you can have what you call the ternary ones, which they've got ternary ones. They are triangular. They've got 3 apexes. Okay, apex, and then you can have what you call the bivariate diagram. Bivariate diagrams, we'll be talking about the Harker diagrams, AFMs, and the basically Harker diagrams. Yeah, basically Harker diagrams. Okay, and then EFM, it's ternary. Okay. They are constructed by plotting the chemical composition of rocks in an igneous rock series in order to show the genetic relationships and the nature of processes that have affected the series. These diagrams allows us to investigate the nature of compositional changes and inform about the elements or the chemical species responsible for the variation when the data are prior ranked following some compositional criteria. Okay, so they are also used to predict the petrogenic history of the rock species. Okay, you will see when we are looking at the Harker diagram why these variation diagrams are important in predicting the petrogenic history of rocks, okay, and also helping us to understand the compositional changes during either fractional crystallization or other geological processes. Okay, but now you must understand the uses of these variation diagrams. So the number one, you can identify the igneous rock series and liquid lines of descendant, okay, or liquid line of descent. And then you can also, they can also be used to predict the composition of the parental magma and also to classify the igneous rocks, okay, into alkaline rich rocks and other rocks. Okay, and then also to identify the magmatic processes responsible for the differentiation. That is the uses. Okay, now but now why this diagram matters? Okay, for example, when we're looking at the Harker diagram, it will tell us more about the chemical evolution. But when we're looking at EFM, it will tell us much about the differentiation trends, and then QFPM, PF, and then it will tell us more about the mineral classification. Okay, so these diagrams, they help us to identify key petrological processes like fractional crystallization, magma mixing, partial melting, and assimilation. Okay, and they also provide insight into magma genesis and tectonic environments. Okay. Now, Harker diagrams, when you're looking at the Harker diagrams, you're just plotting the elements against what you call the silica. Okay. You are having the concentration of an element or oxide on the y-axis, and they are plotted against the silica content on the x-axis. Okay, sorry. Okay, so these are the oldest of the bivariate diagrams. The Harker diagrams, like I said, they are types of what you call the bivariate diagrams, and are the oldest versions. They are very useful to identify the parental magmas. Okay. If these plots show a clear trend or correlation, then all these rocks are probably related or co-magmatic. Okay, they are of the same series. But now, silica content is a good choice to plot against. Why we put it on the x-axis? This is because of the fact that it shows a wide range of values. Okay, it shows a wide range of values from less than 45% in ultramafic rocks to greater than 70% in acidic rocks. Okay. That's why we are plotting this concentration of elements of oxide against the silica, because the silica is the better choice because of it has got the wide range of values. Okay. Then now Harker diagrams, it's very important to show how major oxide change as silica content increases. Okay, and then it is very important because of it illustrates fractional crystallization trends. It also helps identify processes like magma mixing, assimilation, and differentiation, and also show what you call linear or curved trends that hint at magmatic processes or source heterogeneity. Okay, now I wanted to explain this diagram. The liquid line of descent is the chemical trend exhibited by an igneous rock series if And when such a trend is interpreted to represent a change in the chemical composition of the parental magma of this series due to the processes of fractional crystallization. Okay, so now let's look at this trend. Okay, let's look at this trend. What do we know? From this, we are given three assumptions. Rocks are related by fractional. Rocks are related by fractional crystallization. That is the first thing. Another thing is the trend represents the liquid line of descent. Okay, or if you don't understand this long definition, you can just say the liquid line of descendant is defined as the path that the melt composition follows as crystallization form. Okay, and they will be separated from the melt. So it's the path the melt composition follows as crystal form and separate from the melt. Okay, so another thing that we're given is another assumption is that the basalt is the primary magma. It means the basalt is considered the primitive magma, which with more evolved composition derived through differentiation. That is the assumption. Then now, let's look firstly at aluminium, all right? At aluminium oxide. We know aluminium oxide, it shows a slight increase and then now a decrease. But why? We know that initially we are crystallizing what you call the plagioclase. So when we are crystallizing a plage, the plage will take up what you call calcium. Then now it means calcium, it will be removed from the system. So if the calcium is removed from the system, it means we're going to have in that system, we are having what you call the aluminium, we're having what you call the aluminium that is in the content, okay, in the system. Now, that's why the aluminium starts to increase. Initially, it increases first because you are using up more of the calcium to make what you call because this calcium it's the major component in the plagioclases. That's why now the aluminium increases because we are not using this aluminium. But now with time, because you are using more of the calcium, it means the plagioclase crystallization it will decrease or it will be depleted, and then aluminium it will now start to be used up. And then when you are starting to use this aluminium to form a low temperature plagioclases like albite, that's now when you're using this aluminium, that's why aluminium content it will start to decrease. And then now that's why aluminium it will show this trend of increasing first and then decreasing. Okay, so let's stop here for now, and then when we're gonna be continuing, we're gonna explain this magnesium and calcium oxide, sodium, and the potassium one. See you on the other side. Cheers.